Today we're going to talk about the Pythagorean Theorem. You've definitely seen this before, so let's just remind ourselves about it. Okay, so first thing we need to remember is that the Pythagorean Theorem is used to find unknown sides, okay, in a right angle triangle such as this one. Okay, of course this little square tells us it's a right angle, and we have three sides, A and B. Those are sometimes called the legs. Okay, and then we have C, which is of course the hypotenuse. Okay, and the idea is that this side length, which in our picture would be 3, and this side length, we can add the squares of those side lengths, and that gives us this one. Pythagorean theorem looks like this: a squared plus b squared equals c squared. Okay, and the couple things that you need to make sure you remember about this is that C is always the hypotenuse. Which one you write as A and B doesn't actually matter. Like I said, those are both considered the legs of the triangle, the ones that actually touch the right angle. You can, of course, remember the hypotenuse in a couple of ways. It is the longest side. You have to be careful when the triangle's all twisted and turned around, though, that you can tell that it's the longest side. It is also the side that is opposite the right angle. Okay, try not to remember it as a diagonal side because, again, if we twist and turn the triangle around, then you might get confused that way. Now, just looking at this formula very quickly, okay, you might have in grade 7 or grade 8 been taught 3 different formulas depending on what you were trying to solve for, A, B, or C. Here in grade 9, we like to remember one formula for the Pythagorean theorem, and then we're going to use what we know about equations to solve for whichever side we are missing. Okay, so let's go ahead and use the Pythagorean theorem in our first example. Okay, so example 1. We want to label the sides of each triangle and find the unknown side. So the first thing I want you to notice when you look at this triangle is we are actually looking for C, okay? And in this particular example, this is the hypotenuse. That's what I mean when I say label them. So that's our hypotenuse C. We can call this side A and this side B. And again, it doesn't matter which one's A and which one's B. It's just good to label them so you know what you're solving for. Okay, so let's start by, every time you do this, you're going to write out your Pythagorean theorem. So we have a squared plus b squared equals c squared. Okay, let's sub in what we know. We know that a equals 8. We know that b is 6. And we're trying to solve for c. Now, C is on the right-hand side right now, but that's okay. We'll just leave it on the right-hand side. If you really didn't like it, then you could take both sides, this side and this side, and completely flip them around. Okay, so let's start evaluating. We're going to follow BEDMAS, of course, so we're going to deal with our exponents first. 8 squared is 64. Okay, 6 squared is 36, and that equals C squared. 64 plus 36 is 100. Equals c squared. And now we want to continue with opposite operations. Okay, and this is 100 is what c squared equals, but we want just c by itself, so we want to get rid of this square. So we do the opposite, and the opposite in that case is actually called the square root. So we're going to take the square root of 100, and that's going to equal c. Okay, pay attention that you make sure that you're writing just c over there. And of course, if we take the square root of 100, we can do it on our calculator if necessary. We get that the unknown side c is actually 10. Okay? Okay, so let's go ahead and try the next example. Okay, and this, we're just going to take this Pythagorean theorem and we're going to apply it to an example problem. Okay, so here I want to know how high off the ground is Ollie the owl. Okay, so here I have my triangle right here. Of course, it is a right angle triangle down there. Okay, now important to note here again, even though it's a problem, we still want to label our sides even though that wasn't asked. Okay, so right away we're going to notice that this right here is actually C, is our hypotenuse. Okay, and then we have our 2 legs, how high the tree is, what we're looking for, we can call that one A, and let's call that one B, and again, it doesn't matter. Okay, so hopefully you can see the difference already in this problem. In this problem, we are obviously not solving for the hypotenuse because we're given that, so we're going to be solving for one of the side lengths instead. Let's start the same. Let's write out the Pythagorean theorem. Equals c squared. Okay, let's sub in the values we know. We are looking for the a squared, so we'll leave that there. We know that b is 12, and we know that c is 25. Okay, let's go ahead and simplify them. I always find it good to do my exponents at this point. So we know that a squared, and we have 12 squared, which is 144. And then we have 25 squared, which is 625. Okay, now the difference in this one, of course, is that we are now solving for this a value. Okay, so we need to move this added 144 to the other side, and it's of course going to become a subtraction. Okay, so we're going to have 625 minus 144. Okay, and that equals 481. And same as before, we now want to get rid of this squared. Okay, so we do the opposite operation of that, which actually means to square root. So we are going to square root 481. And that will give us approximately 21 point, let's round to one decimal place, 0.9. Okay, so that's the difference in terms of when we are not solving for the hypotenuse, when we're actually solving for one of the side lengths or the legs. Now, one other thing, this is of course an application problem. We're asking how high is the tree or how high is the owl off the ground. So of course, you know that we must have a therefore statement at the very end. Okay, so therefore, Ollie is 21.9 feet high, okay, and the units are what's important there. We can round to one decimal place in general. So thanks for watching, and we'll see you in class tomorrow.